Good evening, everyone. It is Sunday, August 10th, 11:24 p.m. We have two more problems, and I think I'm done with neat code stuff. Advanced dictionaries. Advanced algorithm. My lord, what am I saying? Advanced graphs. Yeah, that's the word I'm looking for. That has been a tricky set of problems. I guess maybe a little bit more than tricky. It's definitely been extremely hard, like set of problems. That's something I'd have to spend more time on in order to get more comfortable with. Um, so yeah, we'll see where we go from here. But I think after these two, I think I'll maybe put a pause on my videos for a little bit and start applying to some places. Maybe I'll bring my videos back in the future. But we'll see. So there is a foreign language which uses the Latin alphabet, but the order among letters is not ABC to Z or Z as in English. You receive a list of non-empty strings called words from the dictionary, where the words are sorted lexicographically, based on the rules of this new language. Derive the order of letters in this language. If the order is invalid, return an empty string. If there are multiple valid orders of letters, return any of them. A string A is lexicographically smaller than a string B if either of the following is true. I'm blanking them. Mm-hmm. What the fuck? Dude, I don't even know where to start. It's interesting that the N comes before the F. Would that not be the case here? Okay, but how does that say? We just know N's greater than H and R, and F's greater than H and R, but we don't know the N's less than F. What? Oh, because it's the third character. Dude, I have actually zero clue on how you even solve this. N plus V plus E. What is N? Ah! Oh my god. You know what? I actually I don't. I'm brain farted. I'm probably just honestly gonna watch
Hey everyone, welcome back, and let's write
explanation.
some more neat code today. So today, let's solve the problem.
I'm not gonna lie. I am so exhausted. I think I'm getting sick right now. So I had a long day today. I'm just gonna let this video kind of play itself.
Problem Alien Dictionary. And yes, this is another problem from the Blind 75 list. This is the problem 32, a graph problem, Alien Dictionary. I've been wanting to do this problem for so long now, and we're finally doing it because now we actually have LeetCode Premium. And again, thank you for all my Patreon supporters for making that possible. So let's get into the problem now. And by the way, the link to this spreadsheet will be in the description if you want to take a look. So this is a pretty hard, by the way, the link to this spreadsheet will be in the description if you want to take a look. So this is a pretty hard problem, I will admit. It's a hard graph problem. So this problem is going to involve the algorithm topological sort that you may or may not have used before. You may not have even heard of this before. Topological sort involves a DAG, a directed acyclical graph, a graph that has directed edges but no cycles. So the premise is we're given a new alien language that uses English alphabet letters. So it's going to be basically lowercase a to lowercase z, but the ordering of these characters is unknown to us. Now we know in regular English, the ordering is basically A, B, C, all the way to Z, right? This is the order, there's 26 characters, but basically they're saying that now we have a different ordering of these characters, and the goal for us is to try to figure it out. And what we're given to figure it out is basically a list of words which happen to be given to us in sorted order. They say lexicographically sorted. That's basically just sorted based on how regular sorting of words works. So our goal is to return a string of the unique characters that were given in this new alien language based on the words that were given. And we're going to return this in sorted order, in increasing order, based on the new language's rules. Now, if there is no solution, we're returning an empty string. So we have to figure out what that even means. What does it mean for there to be no solution? And also, there could possibly be multiple solutions, and if there are, luckily for us, we're allowed to return any of the valid solutions. Now, they tell us that two strings, S and T, S is going to be smaller than T if at the first letter where they differ, the letter in S comes before the letter in T in the alien language. And this is pretty intuitive. Like, if we were given two words such as apple and banana, how are we going to sort these two words? Well, we're going to look at the first character, right? And we see, okay, the first characters are different. And A, we know A is less than B, right? That's how the ordering works in English. So we're going to check just the first differing character. Since A is less than B, that means A comes first in the ordering. So how would we order these words? Basically how they're listed right now. Apple comes before banana. What if we were given a different word, such as apple and ape? Well, in that case, we look at the first characters. Okay, they're the exact same. So we still don't know how to sort them yet, right? We look at the second characters, P, P. They're the exact same. We look at the third characters, P and E, and we know in English the letter E comes before P, right? So the correct ordering of these words is going to be the opposite. It's going to be ape and then apple, right? So that's how we would sort these words. Now, the difference in this problem is that the input that we're given is already sorted, right? So these words are already sorted. So we're going to use that to our advantage to basically figure out the ordering of the characters, character by character. And there's just one edge case we have to worry about. So if we're given two words where they have the exact same prefix, right? Where basically the shorter word is a prefix of the longer word. If that's the case, that means the smaller word is always going to become first in the ordering. So for example, if we had one word ape and another word apes, no matter what, since these words Since this word is basically a prefix of the second word, they match, right? So whatever the longer word is going to be is always going to come after the shorter word. And if that was not the case, what if we were given a list of words where that was not the case? What if we were given apes and then we were given ape? Well, based on what they just told us, that's invalid, right? They say the opposite must be true. So what we can say is if we ever see something like this in our list of words, then we know there's no solution, and that's going to be one case where we return an empty string. So they tell us that this input list of words is supposed to be in sorted order, so we're going to use that to our advantage. And so remember, if these two words are in sorted order, how was it determined that they're in sorted order? How was it determined that this word must come after this word? Well, it must be based on the first differing character, right? That's what lexicographically ordered means. So let's just go, for every pair of words, let's go character by character and find the first differing character and see what kind of information that gives us. So let's look at the first characters. Well, they're the exact same. Let's look at the second characters. They're the exact same. Let's look at the third characters. They're different. We have a T that comes before an F. So that must mean in the alien alphabet, T comes before F. So this is not, in regular English, this isn't true, but in our alien language, this seems to be the case. So let's just keep track of that. Let's just remember, okay, T comes before F. Next, let's look at the next two words. So we're going to look at the first two characters, and immediately they're different. So we know that these two words were sorted based on this first character, and we know that E comes after W because they're in that order. We have a character W, and we know for sure E is going to come after that W. Now, who knows? Maybe there are some characters in between here, right? Maybe it's actually going to be W, F, E, something like that, right? But we don't really know that for sure. All we know so far is this is true and this is true. That's all we can assume from this ordering, right? We know that these first two characters are in that order, but the remainder of the characters might be in any order, right? Because when words are sorted, they're only sorted on the most significant differing character. So now let's look at the next two words. Look at comparing each first character. They're the exact same. Let's go to the next character, R and T. Now they're different. So now we know for sure R comes before T. So let's go ahead and do that in our drawing, right? R comes before T. Now, we see that we already have a T in our graph. And actually, I haven't actually mentioned that this is a graph, but it's starting to get intuitive why we would want to represent these relationships as a graph now, right? We could separately say R, T, but why not include this node that we already have? So we know R comes before T. We know this for sure. Now time to finally look at the last two pair of words. Look at the first two characters, E and R. So that's the first differing pair. So we know that E comes before R, and we know that R is actually already in our graph. So then we can say, okay, let's take this edge and then hook it up over here. So once you recognize that you can use those relationships of characters and the relative order of those characters to build a graph, this problem becomes doable, right? Then all we need to do is now traverse this graph. Now in this example, it's pretty straightforward, right? Clearly we see that the order is non-ambiguous, right? We're going to start with a W, then E, then R, then T, then F, and that's, going to be the entire order. And you can see that this order is also in the output that they gave us in this example. So this matches up pretty easily. So you'd think, okay, at this point the problem is easy, but actually there's a lot of different ways this graph can be represented, and traversing the graph itself is not super intuitive, and there are multiple ways to do it. You can do a BFS solution, a breadth first search solution, or you can do a depth first search solution, and I much prefer the DFS solution. There's so many more like bookkeeping things you need to do with the BFS solution that I don't really think it's worth doing. I think the DFS solution, even though it's recursive, is just so much better, so that's what I'm going to be focusing on. So let's change this problem slightly. Let's say that this F actually pointed at the W. So now, if we were traversing this graph, what the heck would the relative order be? We could start at any node. We could start at R and then say, okay, T, F, W, E, and then we say, okay, we got back to R, so we already visited that. But is that a valid order? Like, this is very ambiguous. It's not that this has multiple solutions. It's that this is invalid. There's a contradiction, right? What if we had a shorter cycle? What if we had, okay, W, and then E comes after W, and then W comes after E? Do you see how that's a contradiction? We can't have opposite rules, right? It's basically like if we had an input list of words that was something like this. We had W, E, and then E, E. So clearly we have a different character here, meaning E comes after W, like this. But then maybe we got that same word, W-E. So how can we say that this list of words is sorted when, the same word is in both positions, and then there's another word in between that? That doesn't make sense. Basically, that's how you know that there's a contradiction. In that case, we return the empty string. There's no real solution, and we know that because there exists a cycle in our graph. Now, what if this last word in our input actually didn't exist? What if we cross it out? In that case, we would never get this connection where E hooks up to R. We have two separate graphs, right? But there's no contradiction here. It's just that now we have multiple solutions. So we could say, okay, the relative order is either we, R, T, F, right? Basically going through this and then doing this one, right? Or we could even do it in the opposite order, R, T, F, right? That's one way. Or we could even do a breadth first search approach, right? Put these two first, WR, then put these two, ET, and then put F, right? All that really matters is that this, like, if there's a connection, if there's a directed edge from this node to this node, all that matters is when we return the output string, this character shows up before this one. And similarly, this character shows up before this one, and this character shows up before this one, etc., etc. We really need to guarantee that that's the case. So at this point, you might think, okay, let's just start at the beginning of each of these components and then just go through it, right? Like say, okay, W, E, R, T, F, and then just build the output string like that. And I'll show you one reason why that's actually not going to work. If we were given an input list of words like this, what we would end up getting is basically a graph that looks like this. And this is a perfectly valid graph, right? What's one valid ordering of this? Well, basically A, B, C, right? That's one valid ordering. But let's say we did a DFS search on this. Let's say we started our DFS here, so we got an A in our output. Then let's say we went to this node first, then we got a C in our output. Then from our DFS, then from A, we see this is the base case. Then we go back up to A. We say, okay, now let's go to B in our DFS. So then we got a solution of A, C, B. Now from our B, what we're gonna end up doing is going to C. So in reality, C should come after B, but we see in our input, it came before B. So basically from our DFS, we got an invalid ordering of this graph. So, if we're doing a DFS from the beginning, how do we know that we should be going down this path down to the B before we go down the C path? Well, the answer is we don't really have a good way of knowing if we're doing this with DFS. But there is a workaround solution to that. And the solution to that is going to be doing a post-order DFS. So in reality, yes, we're going to be starting at this node, but we're not going to be adding it to our output yet. We're going to be adding this to our output last. So, okay, we're here. So now we're going to get to C, right? Now we're at C. Now we're going to go farther down C. We see C does not have any children, right? So that's our base case. So now, since this is post order, now we're going to actually add C to the output. So now we're going to end up popping back to A, right? So we're now back at A. So we're going to continue the DFS. This is post order. Let's do all of our descendants before we process A. So let's go to B. Okay, B, and B has some neighbors down to C. Okay, we see C has already been processed. No need to do that again. So B does not have any more descendants. So now we can process B. Let's add B to the output. And now finally we can process A, right? So what you see is that the way we did it now was not ambiguous, right? We didn't end up, well, we made sure we ended up doing all the leaf nodes, right? The last nodes first, and then these nodes, and then we finally did A last. So what you can see is that we actually built our result in reverse order, which isn't bad because easily we can take this and reverse it, right? So when we get the output of this, we're going to make sure to reverse it before we return it. So we're going to return A, B, C. So that's the main idea of what I'm going to be doing when we're actually writing the code. That's kind of how topological sort is done. That's how I was taught to do it in school. So it's just a DFS, except we're building the result in reverse order. And there's one last thing we're going to have to keep track of, what we're going to be doing for loop detection. And really what we're going to be keeping track of is two things, similar to how I did it in the picture. We're going to be marking if a node has already been visited, meaning it's already been, let's say, processed or whatever. And in this case, what we want to do is map it to, let's say, a set. We could do a list, but a set is going to make sure that we don't have duplicates. So we're
oh crap! Whoops.
Duplicates. So we're going
to imagine.
Nah, I'm gonna keep it in there. Imagine all the people.
We're going to go through for every word in our list of words, and then for every character in each word, we want every character to be mapped to a set. And then we want to go through every pair of words. So for I in range, the number of words that were given minus 1, so that we go through every single pair. Let's get each pair. So word 1 and word 2. Word 1 is going to be the word at index I. Word 2 is going to be the word at index I plus 1. So let's get the minimum length of both of these two words. So let's get the minimum of the length of each of them. And the first thing I'm going to check is basically that base case, that edge case that we first mentioned. So mainly if the minimum length of each word is the exact same, right? Meaning the prefix of the words is the exact same, but the first word is longer than the second word, in which case we know that we have an invalid ordering, right? That's kind of the edge case that they explicitly mentioned. So the length of word 1 is greater than the length of word 2. They have the exact same prefix, meaning that it's an invalid ordering, basically. So in that case, we would have to just return an empty string.
Ooh, you know what? I'm gonna be a scumbag today. I think I'm just gonna go straight to the code and just read it because I'm too confused to even understand what's going on. Cool. Khan's algorithm. Is Khan's close to Kusaraj's? I thought Kusaraj's, or Kusaraj's, what is Kusaraj's for? Kusaraj's algorithm. A linear time algorithm to find the strongly connected components of a DAG. It's to make a component graph? Is that what it's for? For each word, for each character in each word, we're making character set where each character is a set. Okay. So a dictionary. Is it a dictionary of dictionaries? Is that what I'm looking at? Or a dictionary of sets? Oh, okay, yeah, I see. Oh, n degrees. Oh my days. Oh, wow. Hey, this is confusing me. It's not fun for my last... for my second to last problem. Okay, so far for... So we're going to go through each word. We're going to get the current word and the next word. Well, that's not going to work on the last one, huh? Oh, I guess they would, actually, yeah. Yeah. Because the range is exclusive on the end. Not inclusive. Return an empty string. Yeah, I don't know. I want to see, just run that real quick, see how it goes. Okay, so accepts, but why? This is so confusing how this all works. I did not like advanced graphs. They break my mind, I'm not gonna lie. Okay. So they're not equal. That means one has got to be greater than the other. So word 2 has to be less. And let's create the graph. Yeah, way too confusing for me. Not gonna lie, I'm gonna call it there. I'm beat. That did not help my brain at all. And you know what? We got. I'm gonna check that even though I didn't really get anywhere any close. We have this last one here, which is the one we'll be doing tomorrow. The problem is this is another Dijkstra's. Yeah, or Bellman Ford. Fuck. Oh, is this deal with negatives? Come on there. Bellman Ford is like an n cubed algorithm, but it can handle, I believe, negatives where Dijkstra's cannot handle negative paths. Is there negatives on this path? Potential negatives? Does it say? It says it's better than... Okay. I wonder why we use Bellman's then. Bellman's can handle negatives, right? That's what I thought it can. Bellman's is an all-path solution, no? I don't know. Yeah, Alien Dictionary, that one was too confusing for me. Not gonna lie. I'd have to go back there another day. Just not today. But yeah, I mean, sorry for if the disappointing video, late night video, happens. We're all on our path trying to figure things out. So fortunately, that was not intuitive whatsoever to me. I'd have to spend some more time to look into that. But thank you for watching, and I'll see you tomorrow for probably my last video. Alright, have a good night.